Right, everyone's coming in.
Same thread, but you want the water shows. Yeah, so just watch it.
And that's in. Okay.
Hi, Martin.
Right. Hi, everyone.
Hi, everybody.
Hi, everyone. Give us
Hi.
a few seconds
Hello.
just to make sure I've admitted everyone in, and then we'll get started.
De las tres. Necesito que hablen bajito y no gritando como siempre, si no, no digo nada.
Do that. Right, let's get going. So, hi, everyone, and welcome to the next WebTech webinar. My name is Sam Thompson. I'm the Marketing Communications Manager here at WebTech, for those who don't know me, and I'll be your host for today. So today's session will be presented by our Managing Director, Martin Cuthbert, and he'll be talking about optimizing and maintaining hydraulic efficiency on mobile machinery. So this is a presentation Martin's already presented twice. Sorry about that. At IBT in Cologne and Chicago, and so we're running it today. Just a few pieces of housekeeping before we get going. I've disabled cameras so that it helps with bandwidth for everyone. But if I could ask you to remain on mute during the presentation, please, and that'll be much appreciated. If you do have any questions during the presentation, if you can put them in the chat, please, and I'll address them at the end. And then at the end we will have some time. So if you have any questions at the end of the presentation, if you could, feel free to take yourself off mute and ask the questions there, and we'll go from there. So that's everything from me, and so Martin, I'll pass over to yourself to get going.
Okay, thank you very much, Sam. Welcome everybody. Good morning, good afternoon, good evening, wherever you are in the world. It's our privilege to give this webinar today. As Sam mentioned, we gave this at the IVT, the Industrial Vehicle Technology Show in Germany and in Chicago last month. That show's interesting because it's talking about the next generation of machines. It's looking at a lot of electrification, running machines on batteries, replacing diesel engines with electric motors. What I find interesting is that almost invariably they're still using a hydraulic system to transmit the power. So we'll be talking today a bit about optimizing and maintaining hydraulic efficiency and using an example of a sort of next generation machine. But what we talk about is relevant really to all mobile hydraulics, and if you're actually an industrial hydraulics person, not a mobile person, it's relevant there as well. The other person I'd like to welcome today is Steve Skinner, who's also on the call. And when we get to the end, if you have any questions, I'd also invite Steve Skinner to help field any of those questions. Steve has helped us a lot with our training material, has a wealth of knowledge in the industry, and used to be Eaton's lead hydraulic trainer in the UK. So, right, without further ado, we will tell you a bit about this company, this construction machinery company that wants to build a next generation machine. And to do that, they have three decision makers. And decision makers are there to design this new autonomous dumper truck. But as mentioned before, the principles could apply to any mobile machine. And the lead engineer on that is Declan. And he's responsible for designing the machine, mechanical design, including the hydraulics. And he works alongside a product manager. And the product manager is Paula, and she's responsible for promoting this product in the field and making sure that it stacks up well against the competitors. And then last but by no means least, Steve is the service engineer. He's got a wealth of knowledge from servicing and maintaining the existing machines in the field, and he's using that to advise the other two about what best practice might look like in terms of maintaining this new machine. And overall, their aim is to produce a mobile hydraulic machine which has got lower energy consumption, has got reduced downtime, and has got increased output. And they all work for one man, Wim, who's the CEO of their company, and he has very big ambitions for this next generation machine. And he's the sort of man who doesn't go for a walk. He wants to climb Everest, and he has an Everest-like ambition for his company and for this new designer machine in the next few years. And his ambition can sort of be depicted by that's how many machines he's expecting to sell in the first few weeks. And so that's his objective in all of it. And that challenge, if you like, is reflected back on the three decision makers. And so Declan, Paula and Steve are all looking at that and thinking, okay, so what does that mean for me if we've got that objective to design that machine and we've got that pressure being put on us by our CEO, what does that mean? And so for Declan's aim is how can I design a machine which has got lower CO2 emissions and a lower cost of sale? And Paula's thinking about it and saying, okay, so if we don't do something, our competitors could overtake us. And Steve's looking at it a bit more philosophical and saying, well, by the time we've launched it, another year will have passed, and we ought to be better and we ought to be more sustainable. So how can we achieve that? And ultimately, they all know that their CEO, Wim, is counting on them. So how can WebTech help? Well, if you look in the bottom right-hand corner of the presentation today, you'll see a little word, a little number 60. We are celebrating our 60th anniversary this year, and we've been in the instrumentation business really since the early 70s. And over many years, we have supplied test equipment to all different sorts of end users and OEMs in the agricultural, the construction, the mining, and many other mobile machine areas. And we understand that there are conflicting needs for test equipment and conflicting challenges that people have. And some of them are shown there on the screen. Most often it's driven by reducing downtime. It could be that the manufacturer's got a warranty issue or an issue where they're not sure and can't prove whether it's warranty or not. It may be that the design engineer wants to improve control on the machine, looking at the machine efficiency or a particular component efficiency, improving safety, monitoring pump health. So there could be a whole different set of reasons there. And to best approach this, we've come up with a three-step plan. And the first step of that is to ask the question, which combination of maintenance is most appropriate for your machine? And there's a machine on the screen there, which I think if we don't own one like that, we've certainly had one in the past, and we'll recognize that when something happens on that car, then we will take action. If the first thing we could perhaps look at is what happens if the wiper blade starts smearing or a light bulb blows, then the most likely thing is that we will go out and purchase a spare. We may have a spare with us, and we would make that change. We'd replace that when it happens, and we would call that reactive maintenance. There are other things on the car where it would be dangerous to wait until they fail, and we look at a couple of examples like the cam belt or the oil or the filters. We would tend to preventatively do those by changing them before they've failed. You take something like the cam belt, different cars will have different periods of time for when they're changed. Maybe it's 100,000 kilometers, sort of 60, 80,000 miles. There'll be a whole load of data behind that to say this is the time when we've maximized the life of that component and it hasn't yet failed, and that's the best time to change it. So mentioned, they would be considered to be preventive maintenance approaches. There are other components on the system, on the car, where we might be able to monitor them in real time. Certainly on many modern cars, you can monitor brake pad wear and tire pressure. And that kind of makes sense because it depends how you brake and how often you drive the car and how bumpy the road is maybe as to when you might need to change those or to pump the tires up. And that we would call predictive maintenance. And then last but not least, sometimes things don't go to plan. You're driving behind a truck and it sheds a load of bricks and you hit a brick and burst a tire. Then you'd be carrying most likely either a spare wheel or a run flat tire. And that we would term a form of proactive maintenance. So there we have a combination of different maintenance approaches, which perhaps before we showed this on the screen, you hadn't thought about it like that before, but we're using different approaches for different components depending on how critical they are. And we can depict that on a little logic tree where on the top left-hand corner in green, we can ask the question, can we stop it going wrong in the first place? So a proactive approach. And if the answer is yes, that we can do that both effectively and affordably, then great, we're on the straight and narrow for a planned maintenance strategy. If we can't do that, then we ask the next question, can we monitor its condition? And that would be a predictive maintenance approach like we were with the tyres. And if we can affordably and effectively do that, then yes, we're still on a planned maintenance approach. If that doesn't apply, then we go to preventive maintenance. Can we predict when it will fail? I.e., do we have reliable, repeatable data about a particular component life? And if the answer is yes, we can do that efficiently and effectively. Then we've still got all the tools there for a planned maintenance approach. However, if we can't do any of those three things, we're left with reactive maintenance, to which the best solution is probably just stock up with spare parts. And the clever thing there is probably having the right spare parts in the right place for when that happens. And we would term that a troubleshooting approach. And really the name here of improving the efficiency of the machine is to reduce downtime, is to move as many things to planned maintenance as possible and reduce the need for troubleshooting. So if we were to look at that with the example of a conveyor hydraulic system, you can see on the screen now, we could take that philosophy of different types of maintenance could be used for different parts of the circuit, like we did for the car, and apply it here to the hydraulic circuit. And we could color code them accordingly, depending on which approach was most suitable. So if we look here, and we've got three different colors, so preventive in blue, predictive in green, and proactive in pink. And so if we were to take the preventive to start with, you'll see that the hoses in the hydraulic circuit have been labeled in blue. It seems to make sense because we could take a view that after so many months or years of usage or so many thousands of hours of running a machine, we will just go around and change those hoses as a matter of course. Compared to other components in the system, they're relatively low cost, and compared to the cost of downtime if they were to fail. If we were to look at the opportunities for predictive maintenance, then you can see in green there, we've got some flow meters and pressure transducers, we've got some speed sensors and some level sensors on there. And so they're there to do some continuous monitoring and help us predict whether any component is in need of maintenance. And then lastly, in pink, we've got some proactive maintenance being applied in a couple of different ways there. So on the left, you can see that this circuit must be really critical because the whole of that hydraulic pump circuit has been duplicated into the pink area on the left. Perhaps this conveyor belt circuit is being used in the mining industry, where the cost of downtime might run into the hundreds or more thousands of dollars per hour. And therefore, if that were to fail, they would just switch over onto the backup circuit and run that instead. Clearly, that depends on the application. Not every industry could afford that. The other proactive maintenance that's being run there on top of the tank, you can see there's a kidney loop filter circuit to optimize oil cleanliness and to prevent that then causing other issues in the circuit. So you can see there the example of taking that approach of which type of maintenance is most appropriate for which component and then applying it to the circuit. If we were to look at another way of deciding which approach is most suitable for which part of the circuit, this graph here shows across the x-axis, across the bottom, what's the cost of the maintenance equipment. So what's the upfront cost of the equipment, and then up the y-axis, what's the downtime cost or the inconvenience if the system were to break down. And you can see a couple of examples on there. So if our TV remote control breaks down, So what, we have to stand up and go and switch the television on or change channel. We nip to the shops and buy some batteries and change them. And we'd consider that then a reactive approach, relatively small cost to hold the batteries in stock, or to go and the cost of downtime is very small. The extreme at the other end is the nuclear reactor. Can't fail. We have lots of redundancy and lots of planned maintenance built into that. I suspect for pretty much everybody on the call, their situation will sit somewhere between the TV remote control and the nuclear reactor, and therefore the exact cost of downtime will depend on the circumstances. I mentioned before, if it's mining machinery, something like that, it could be very high. If it's a situation where you have, I don't know, 10 trucks in the yard and you don't use any of them, and you need to use one and it doesn't work, you move to the next one or the next one, that's fine. Maybe the cost of the inconvenience is relatively low. So that's for a question that we would often ask a customer is, say, so why does it matter if there's downtime? And we then find that for some customers it doesn't, and for some it's really critical. You can see on the right, depending what the answer is there helps dictate what the budget is for the maintenance equipment. And so the budget for the nuclear reactor is clearly much higher than the budget for something where downtime costs very little. And the approach that you might use can change accordingly. So more proactive maintenance, more predictive maintenance, where you've got very high cost of downtime, you're more likely to be leaving it to reactive and a bit of preventative maintenance if the downtime's low. In my experience of visiting different customers, that logic doesn't always hold out. And I think that's because the people in charge of the budget for maintenance equipment aren't always privy to what the downtime cost or the inconvenience is. And somehow, even though the downtime is very high, there doesn't seem to be a willingness or an ability to invest in maintenance. So sometimes the theory breaks down, but I think the theory is still good. And as you can see, coming up, we can see how we can apply this in terms of the maintenance equipment that you might use. So if we just summarize what we've just talked about, so the 4 types of maintenance: reactive, wait for it to go wrong, then fix it; preventive, estimate when it'll go wrong and fix it before it does; predictive, monitor its condition and fix it when necessary; and proactive, try to stop it going wrong or minimize the consequences of a failure. So what I'd like to do now is take you on to step 2. So the first step was to look at the combination of maintenance. The next step is to consider what tools might be suitable for carrying out maintenance. Select a standard or custom tool, and you can see a whole array of different sensors and instruments on the screen there, many of which WebTech manufacture, measuring flows and pressures and temperatures and speeds and frequencies, etc. And you go, well, that's a bit of an overwhelming range of different equipment there. Which one would I use when? Well, to answer that, we would ask 3 questions. And the first question is, why is it important to measure something? So why is it important to know the pressure, or why is it important to know the flow or the temperature in that particular part of the circuit? And what are you going to do differently? So the next question will then be what? What are you going to do differently now that you have that knowledge? And that, in my experience, depends a little bit on who you're asking and what their involvement with the machine is. If you're asking one of the design engineers, and I can say this because I've been in that seat in the past, well, it's interesting. I want to know that because it'd be interesting to know what it is. Are you going to do anything differently? Probably not. Well, that's not a great reason for investing in putting that sensor onto the machine. However, if you are going to do something with that information, the next question would be, who are you expecting to collect or interpret that information? Because that might decide whether it has a screen or not, whether you're just collecting something and feeding it electrically back to a PLC, or whether you just want a visual display, or whether you want to be data logging information and then maybe you're sending it off somewhere else to interpret it. Certainly a lot of the experience we've had when working with mobile machinery OEMs with the dealers and their dealer tools is they often want to data log things, and then they've got evidence which they can send back to the main service center. They can use that for looking for warranty failures, but they can also then compare the data with other data coming in from other dealers and look for patterns and maybe help the dealer interpret what that means. So they're the questions: why, what, and who on the different tools. So what we'd like to do now is just share a few examples, if you like, for each of those different maintenance approaches. So the first example, reactive, wait for it to go wrong and fix it. Still seems to be a lot of people in our industry that take that approach. Why do we know that? We know that because they'll often come to us and buy a piece of equipment like you see in the top right there, portable hydraulic tester. As an emergency purchase, the machine's broken down. This example here, we've got a screening and crushing machine. Machine's broken down. They want to know what it is that could have gone wrong. And so they're starting there with troubleshooting. So they'll lift the lid and have a look at the engine and the hydraulics attached to it. And then we'll start measuring. And normally the first place to start, say, okay, is the pump working? And so here we can see the portable hydraulic tester. It measures flow, pressure, and temperature. It's got a load valve in the bottom of it. You can see there, which enables us to measure the output from that pump and then load the pump progressively to simulate its normal working conditions, and then test to see whether the pump is delivering the correct flows or not at different pressures. You may, depending where you put it in the circuit, also use it to test whether there's leakage across the relief valve or whether the relief valve cracking pressure has been set correctly. What would you do with that information? Well, if you've got a new pump, you would know what its volumetric efficiency was. If you're testing the existing pump, you could draw a comparison and say, okay, as I load the pressure in the system, how much does the flow decrease? And is that decrease acceptable? And if not, maybe that's the problem. If it's okay, then you move on to another component in the circuit and see why the machine's not working correctly. And so that's a classic troubleshooting approach. And the portable hydraulic tester is probably the best known tool that we manufacture. And a lot of people would relate to that. There are lots of different sizes and versions of that available. How does it work? Well, it has inside it a flow meter, a pressure gauge attached to a shuttle valve. So depending, regardless of which direction the flow is going through, it will always show the highest pressure. It's also got a temperature sensor in it. And then it has Webtec's Interpass system to protect it from overpressurization. Because you've got a load valve in there, you can pressurize it, and it means it prevents it from going over the operating pressure of the tester. So there's a first example for the sort of tool that could be used. It's not the only one, but it's perhaps the most popular one that's used for reactive maintenance. If we look at the next maintenance philosophy of preventive maintenance, estimate when it will go wrong and fix it before it does. And to do this, we'll look at some data on some pumps. So this is some real data on the lifespan of piston pumps from excavators. And you can see there by the red bars, that's the number of failures that have been had at different life, so measured in thousands of hours. And you can look on the left-hand side and you see there's quite a high peak. So there's 6 units that failed basically at startup, and then there's 3, and then there's another 3. You go, well, why might that be? And often, from a hydraulics point of view, that will probably be down to poor commissioning, poor installation, and we'll go, okay, we can address that through training. Maybe the people who fitted them hadn't been trained correctly, and so let's assume that we can train people, and that will stop that happening. Then we're left with a fairly standard distribution for a hydraulic component. We saw the most failures are around sort of 8,000–9,000 hours, and we've got some before and some afterwards. And so from a preventive maintenance point of view, the question is, when do you replace it? If you take it out early, then really safe, then none of them will have failed, but equally we'll be taking out potentially piston pumps that have still got 3,000, 4,000, 5,000 hours worth of life left in them and throwing them away. So, and on the flip side, if we do it too late, then potentially quite a lot of the pumps have already failed before we replace them. So that's the classic challenge where we need repeatable, reliable data in order to make that decision on preventative maintenance. What tools could we use? So we've drawn 3 examples here. A sort of level 1 situation may not be just about a pump. It may be another situation on a machine where you just want to measure pressures. Here's the example of an HPM 110 with data logging built into it. You could just screw it onto a pressure test point somewhere on the machine, leave it on there for 24 hours, data log the pressures, and then download the data. And that would give you an idea of pressure spikes, pressure variation in the system, which in itself could tell you a little bit about the health of the system, how often you're getting those peaks. Allow you to compare that to last time. Maybe it's the test you carry out every month or every 6 months, and you compare it to last time and go, has it got better? Has it got worse? Is it still the same? What does that tell me about the health of the system and what I might need to change? If the system's slightly more complicated than that, what we've called a level 2 situation, and we're back here at the screening machine, maybe it's for setup, but it could be involved for fault finding. Here's an example of an HPM 4000. It's got 3 sensors, 6 channels, any combination of flows, pressures and temperatures, and use that to ascertain what the problems might be on the machine, or whether the health of the machine has deteriorated since last time. And then for a more complex system where the 3 aren't enough, so I mentioned there that you've still got USB ability to put a USB stick in and store the data, download it and compare it to last time. Then the third example would be perhaps here's a high inertia system. We have counterbalance valves, a more complex machine, maybe a prototype machine, where you want to be measuring 10, 20, 30, 40 different things at the same time, maybe overlaying, you see their flows and pressures against time, and then comparing that performance to a previous version of the machine or another machine that's in use somewhere. So there's the range of tools that are available, if you like, for carrying out preventive maintenance, whether it's just one pressure or right up to 50 channels here of all sorts of different things, including custom sensors if people wanted to feed those in, whether they're analog sensors or J1939 sensors. So we've covered the first 2 maintenance philosophies, the reactive and preventive. The third one, predictive, monitor its condition and fix it when necessary. This is an entirely different ethos, really. So if you look at reactive and preventive, we've been talking really about using maintenance equipment that we break into the circuit with, we carry out a test, we diagnose a fault, or we diagnose a situation, and then we remove the equipment again. With predictive, we're talking about condition monitoring. And so this is much more about permanent installation. And if you look at this example here for the performance of a hydraulic pump, the situation on the left-hand side is meant to indicate its as new status, and then time carries over to the right. And you can see that if you start operating the pump, its performance tracks pretty much close to new pump performance for a long time. And there'll be very, very little degradation over a long time, assuming you've got good, clean oil inside it, until a point when it will start to degrade much faster. And that's the point you want to catch, because it's that moment that you've both maximized the life of the pump, but you've prevented a situation where you might get catastrophic failure. And so that point there, you're only going to get if you're monitoring something continuously, or you're very lucky with your intermittent monitoring. And the way to do that would be to install, as mentioned, a sensor into the circuit permanently. And so here you can see we've got an online flow meter, also measuring temperature. You could also measure pressure consistently, and feed that information into a PLC and use that to monitor the circuit. How does that help you? Example here, you can see it could be permanently installed on the machine. That gives the opportunity to transmit data. A lot of the modern machines now have a telematic system to feed data to the cloud, and then run various dashboards and alarms from that to warn of a problem by predicting problems before they happen. One of the advantages, we talk to customers about this, is it's not just about waiting for things to go wrong. It's also about improving the performance of the machine while it's running. And so if you've got sensors permanently installed on a machine, they can be used for other things at the same time. And so it could be about monitoring pump efficiency. It could be overall energy efficiency of the machine. Certainly the conversations we've had with manufacturers who are now moving away from a diesel powertrain to an electrical motor, maybe got the batteries on the machine. They're looking, how long will the batteries last for? Well, that depends on how much power you're consuming, which will depend on what you're digging or how the machine's being used. So if you can measure the flow and the pressure being used in the hydraulic system, then you've got the hydraulic power being used. If you know what the efficiency is, then that will tell you how much power is being pulled electrically from the batteries. So there are other opportunities around condition monitoring, maybe looking for safety, i.e. is there flow there or not? Is it safe to access the machine? Could also be around cycle times, how quickly is the machine operating? It could be around closed loop control. So there's various opportunities that come about once you start adding the sensor to the machine. So we've covered the first three. I think it's worth touching on proactive. Try to stop it going wrong or minimize the consequences of a failure. We talked earlier on about building redundancy. Clearly that's an expensive solution. Another form of proactive is around pre-dispatch inspection or commissioning of systems. And there it's worth reflecting on that we have a lot of customers that would do this. Using a portable hydraulic tester here to assess the flows and pressures being provided by the excavator to the attachment. It could be a hammer or breaker. It could be a screening attachment. If they're not set up correctly and haven't got the right flows and pressures going to them, then they're not going to operate correctly. It's going to be a warranty issue for somebody, or it may potentially degrade the performance of the excavator. And so that idea of proactively commissioning and testing something every time it's used reduces the need for intervention later on. And we certainly have a lot of customers who do that, and it's their USP in the market, if you like, that they offer that customer service because they know that the customer gets much better performance out of the attachment afterwards. If we were to look at a piston pump that might need setting up, so presetting the pump displacement limiter, you can see the Qmax there, or the standby pressure for the load sensing, or the pressure compensator. All of those things would need setting, and if you can set those up in advance and prove that they're set up, then that reduces the chance of having an issue later on, which might cause some downtime. And so you can see examples there of setting up the maximum flow on the left-hand graph, or the standby pressure in the center one, or the compensator pressure. Again, you could use the portable hydraulic tester. There are a whole raft of different tools you could use. If you wanted to do it graphically, you could use a data logger and actually recreate those curves almost, and prove that you've set them up correctly, set the pump up correctly before handing it over to the customer. So that's just a couple of examples of proactive maintenance. So if we just reflect back, we talked about reactive, wait for it to go wrong, then fix it. Preventive, estimate when it'll go wrong and fix it before it does. Predictive, monitor its condition and fix it when necessary. And proactive, try to stop it going wrong or minimize the consequences of failure. So we talked about the two approaches, the three-step plan. Then just to reflect back, first of all, I'm saying assess the best maintenance combination. The four we've just gone through. Two, select standard or custom tools. We're asking those questions. Why is it important? What would we do differently? And who are we expecting to collect the data or interpret it? And then thirdly, from WebTech's point of view, give lifetime support. We're here to answer questions. We're privileged in that we design and manufacture these products, so we're pretty well placed to be able to answer any questions around them. From the point of view of the three decision makers involved in designing the next generation machine, they were looking to produce a machine which had lower energy consumption, reduced downtime and increased output. They can now look at that approach, if you like, and go, we understand now that we're more confident about how we might plan the maintenance. And from Steve's point of view, he can actually plan the maintenance. And I guess from their point of view, Vim can count on them. Okay, we're coming to the end of the presentation. Just to reflect on some of the products that we talked about on the way through. As I mentioned, with the DHT being used there for proactive and reactive maintenance, the data loggers for preventive, could also be used for proactive maintenance, and then the CTA there, permanent installation, can be used for predictive maintenance. Sam's kindly put some QR codes in next to them if you want to find out any more about them. That will take you straight to the website and to the relevant information. Just so we were putting this information together, we reflected on the fact that actually all three of those products have either been recently launched or recently updated in the last few months or about to launch. There's more information coming, for example, on the CTA. There's a milliamp version coming. The data logger there is the HPM 5000. There's a new version, smaller than the one, the HPM 7000 you saw earlier. And the DHT has just recently been updated as well. To find out about any of that, you can go to our website and you'll see information there. If you want to find out a bit more about the different maintenance approaches and the reactive, preventive, predictive and proactive maintenance, and perhaps reflect on how well you do that in your company and what else you could do differently, there's just a very short questionnaire there that shares some answers with you, scores you, and then takes you through to some other free tools that are available to help around training and advice. To get to that, you can scan the QR code on the right hand side. Okay, I think that takes us through to any questions.
Thanks, Martin. Thank you. We haven't had any questions in the chat yet. Just as we finish off, as well as what Martin's mentioned about links to products and the quiz, I've just put into the chat some links to some case studies talking about different examples of the maintenance and how it's helped people. So they're in the chat if you want to click through and have a read of those. I can also send them out as well. If anyone has any questions and wants to ask them now, then feel free to unmute yourself and ask the question if you have any.
Yeah, hi Martin, this is Con Crandall, Stealth Corporation Australia. Nice presentation, thank you. And
hi there.
Happy 60th birthday.
Thanks, Con.
Yeah, I've been selling the blue boxes for, well, I've been with Stealth 34 years. So how much longer is the product going to be tried and tested and proven?
I think as long as people keep demanding it, we're going to keep on making it. And
Yes.
and as we mentioned, we've just given it an overhaul this year, and listened to feedback from people about how it can be improved and made some improvements to it. But fundamentally, it's still measuring flow pressure and temperature. Still got a loading valve in it. It's got safety discs in it, and there still seems to be demand for that as a kind of all-round tool.
It's incredible product. It sells well in Australia, and it keeps going. It's incredible. Such a simple device as well.
Yeah, indeed. It's testament to how long that it's been around, different variations of it. But I think from our point of view, the hope is that it's not just being used for reactive, which is what it was always used to start with, but more and more it's used proactively, and that people are going, okay, let's commission or do some pre-dispatch inspection on a machine and test that it's performing the way it should be, rather than saying, right, I'm going to wait until something's broken and then I'm going to go and see if I can work out what's, to carry out troubleshooting.
Absolutely. That's great. Oh, thanks for that. And again, congratulations.
Thanks, Colin.
Okay. Cheers.
Okay, thanks. Okay, I'll give it another few seconds, just if anyone else has any. Just while we wait, there will be a recording sent out shortly, so you can rewatch, or if anyone who hasn't joined can watch it if they've registered. I will also send out a very quick short survey, either later today or tomorrow. I'd be really grateful if you could fill it in for me, please. Just helps us to improve, as we are planning to do more of these in the coming months and into next year. So keep an eye out for more of these. We are continuing to come up with ideas, and feedback is really important in how we improve it. And I'll also include the links to the case studies into that email as well, so if you haven't looked at them. So okay, Martin, I don't think there's any more questions in there, so I think we can come to a close there.
Okay.
Thank you again.
Thanks so much for your time, everybody. Yeah, appreciate you joining us.
Cheers.
Thank you.
Cheers. Thanks, Sam. Thanks, Martin.
Bye-bye.